Okay, so section 4.2 deals with area underneath a curve. So the idea is that if you're given a graph, then within a certain interval you're going to try to figure out what the area is underneath that graph from within the interval a to b. If you can recall what sigma notation is, that's a very prominent part in this section, where it's basically just the idea that you're given that starting value and then the number of I guess summations they want, and then you'd have a function right here, and pretty much if this started at 1, you would just plug in the first one, the second one, the third one, and so on until you got to the nth term. So just a small little refresher example. I equals 1, we want the sum of the first 5, so and the function is 2x, so in order to find the sum you would just do 2 times 1, 2 times 2, 2 times 3, 2 times 4, and 2 times 5, and add those up. Now how we will use it in this chapter, like I said, we are going to be given a curve, and what we're going to try to determine is the area underneath that curve within a certain interval a to b. So this is going to be done by making a series of rectangles underneath the curve, and that will give us an approximation of what the answer will be. In order to do that, we're going to be looking at the width, which I just labeled right here as x. That might be too small, but that's x right there, and then you will be finding the y values that correspond to that particular rectangle, and then we'll be using the sigma notation to add up a certain n number of rectangles, and then through that we can find out the area that's underneath the curve. Some summation formulas that you'll need to be aware of are as follows. It's just pretty much substitution formulas, and you'll see these applied. You'll see a couple of these applied in the examples I have. But yeah, these four, commit them to memory, just simple as that. And so with that, I'll move on to the first example. So the sum 20 I equals 1 I minus 1 squared. Now the basic idea of these summation formulas and finding the area under the curve is, when you're given this, your goal is to get rid of all of your i's. So in order to do that, you'll be using these formulas right here. Notice how you're given a certain situation where there's an I present, and then what you're actually converting it to is an equation, an expression with n's in it. Except for number 1, that's just c is some constant, and then c times n, so just that constant times the number of rectangles. Alright, so the first thing I would do with this one is just change this into a polynomial. So you get I squared minus 2I plus 1. And then when you have something like this that's straightforward and it's in a polynomial form, and then you've got the summation sign out in front, what you can actually do is you can separate these into parts, and from this you can actually make 3 summation formulas. And then so you can take the sum of each of these parts and then add up all of those together. So this of I squared plus the sum of negative 2I plus the sum 1. What I'm actually going to do now is, just because this is a constant, I'm going to pull this negative 2 out in front so that I only have to deal with the I right there. So that gives us 20 I squared minus 2 I plus, and then this is just going to be the same. Now this is where those summation formulas are going to come into play. For this first one we have an I squared, so we're going to be using number 3 right here. We've got, in this case, our n is 20, so instead of putting in an n, we can substitute 20 for that, and then this entire piece just converts to this. So you're going to drop this summation sign also. So what you'll have is 20 times 20 plus 1 times 2 times 20 plus 1, all divided by 6, minus 2 times, that's just from right here, minus 2 times, and now we can make a substitution for I. So the substitution for I is n times n plus 1 all over 2. So we can substitute our 20 in for n, and we get 20 times 20 plus 1, all divided by 2. And our final piece is plus the sum from I equals 1 to 20 of 1. This is where number 1 would come into play. Our constant in this case is 1. That's our C value, and then our n equals 20. So 1 times 20, that's going to be plus 20. Now that we've gotten rid of all of our i's and even all of our n's, we can just solve this with our calculator, and after doing all of the math and distributing and FOIL and all that, your answer comes out to be 2,470. And that's going to represent the area that's the area of this function within that interval. From one rectangle to the 20th rectangle. Second example, we're going to evaluate the sum of I equals 1, n at the top of I plus 1 over n squared. Now remember that what you're going to be trying to do is get your n's separate from your I, and you want to keep the I. You want to try to keep the I on the right side of the sigma notation so that you can use one of those substitutions. So in this case, the first step is going to be just separate out your n's and your i's. As you can see, if you were to multiply these back across, you'd come up with the same thing right here. From there, you can pull this out in front of the sigma, since what we're trying to do is isolate I on the right side of the sigma notation. So we now have 1 over n squared times sum I plus 1. And then once again, we can separate this part out, this part, into two summation problems. So it would be sum sigma I plus sigma n, like that. Make a substitution for I for this first one right here. So that gives us, because we don't have a specified value for n, we're just going to leave it as n. So n times n plus 1 over 2 plus, and then this applies for rule number 1. In this case, 1 is c, and then n stays n, so n times 1 is just n. Do a little bit of distributing on the inside of the brackets. You can change this n right here in order to get the common denominator as your first term. You can change that to 2n over 2. I'm just going to move the problem up to right here. So now you're left with 1 over n squared times n squared plus, combine these like terms since you have common denominators now, so plus 3n all over 2. Multiply across and you get n squared plus 3n over 2n squared. And then if you can recall the way that what we'll do to find the actual area now is we'll apply a limit to this, and this will actually be talked about more in the following videos, but you set a limit as n approaches infinity to this function. And if you can recall, when you have equal powers in the numerator and denominator, then the answer is just going to be a ratio of the coefficients of those variables. So the answer in this case is going to be 1/2. That's a pretty long video, but this is a big section of chapter 4, and keep in mind that this is the extended way. This is it's the equivalent to the limit process for derivatives, except this is for integrals.